This is the Module 1 end of module test review tour. I hope you're not feeling like this guy and your effort has not yet timed out. As we approach the end of the module, it's time for the finish line face, where grimace meets smile. Just think, you're almost there. The pain of the effort will be worth the pride you feel in your achievement. Enrique built a new gate for the fence enclosing his yard and needs to paint it. In half an hour, the gate is 1/3 of the way covered in paint. Number 1, what is the rate at which Enrique is painting the gate per hour? So we'll present two strategies to approach this problem. One, a visual model of the gate, and we'll see how that translates to a strategy involving equivalent rates. So we can see here that Enrique has been working for 1/2 hour, and at that point 1/3 of the gate is painted. Here, this model translates to this rate: 1/3 gates per 1/2 hour. So now we look back to the question. It says, what is the rate at which Enrique is painting the gate per hour? And so that language per hour translates to over 1 hour, or a denominator of 1 hour. So when another increment of time goes by, so when we get to 1 hour, a half hour has passed, and so he'll paint another 1/3 of the gate. Their equivalent rate, we set that equal to 1 hour. 1/2 times 2 equals 1 hour. We would multiply 1/3 times 2 and find the rate: 2/3 gates per hour. Here's our answer to question 1: 2/3 gates per hour. The work that we did in question 1 can help us to answer question 2. Write an equation that represents the relationship between gates painted Y in X hours. So when you see the equation, you might already be thinking Y equals KX. Now to write that equation, step 1, we need to determine the constant proportionality K. And if we look at our work from question 1, we've already calculated the constant proportionality K. We just need to know where to look and find it. Two places we can look for K is in a table and think about what X value always travels along with K. We can also search for K in a rate: Y divided by X, gates per hours. What is the denominator? What denominator always travels with K? So K's traveling companion is always 1. So when X is 1 in a proportional relationship, Y is K, So in this case, when hours is 1, Enrique is painted 2/3 gates. So K is 2/3. And then 1 is the denominator when K is the numerator. So when X is 1 hour, K is 2/3. So when we have our structure Y is equal to KX, it's simply a matter of leaving a space open for K, the specific constant that describes the relationship between the gates painted in Y in X hours. So then we will just put K into its place. So we can bring that from wherever we found it. But the equation is Y equals 2/3 X. So for the gates painted is equal to 2/3 gates for every 1 hour, X. So each question in this Enrique painted gate series builds on one another. What we found in question 1, we used in question 2. So what we found in question 2, we can use in question 3. It can either be good or dangerous. If we miss something earlier on, that's going to cause us problems in each of the following questions. Question 3. How long will it take Enrique to paint the entire gate? So let's think of where we last left Enrique in question 1. He had the job 2/3 of the way done. So he needs to paint a final third of the fence to have one whole fence, or 3 out of thirds painted. So how much time will go by? See that another half hour is going to go by. For each third, it takes him 1/2 hour. So he will have painted the entire fence in 1 1/2 hours, or 1 5/10 hours. A blueprint for a new school shows a large rectangular parking lot. 3 centimeters of length in the blueprint corresponds to 150 meters in actual length. Number 4, what is the scale factor of the blueprint? And one important unit conversion we need to know is that 1 meter is equal to 100 centimeters. And one important detail we remember about the scale factor is that it is a ratio of units or ratio of lengths in the same units. So here's our goal, to compare in this ratio notation inches to inches. So how would we reach our goal? So here's a path laid out to our goal. It's really a series of equivalent ratios. So if we think that the actual length is y, and the length on the blueprint is x, we can use y divided by x. We can divide the actual length by the length on the blueprint. So go ahead and think about what the numerator and denominator are, and then the missing numerators to get us to our goal. I can't believe I made it that far through the video with having inches written here when the problem clearly involves centimeters and meters. So we're not comparing inches to inches, we're comparing centimeters to centimeters. And now, if we use our conversion, 1 meter equals 100 centimeters, we have 150 to 3, 50 meters to 1 centimeter. It would be 5,000 centimeters to 1 centimeter. So here is our scale factor. 1 centimeter on the blueprints corresponds to 5,000 centimeters of actual length. Question 5. If the dimensions of the parking lot in the blueprint are 15 centimeters by 10 centimeters, what are the actual dimensions in meters of the rectangular parking lot? So this is a diagram of our parking lot on paper, 15 centimeters to 10 centimeters. Now if we were to build this parking lot, we have to think, well, what would be the dimensions of this parking lot that obviously would be way bigger than could fit on our piece of paper or screen. So what would be the dimensions of the parking lot in real life in meters? And think about how the work that we did in question 4 can be useful to us. So which one of our equivalent rates or equivalent ratios could we use to find the actual dimensions in meters? If you said that this rate, for every 1 centimeter on the blueprints, there are 50 meters in actual length, then that could be useful to us. We could multiply 10 centimeters by 50 and 15 centimeters by 50 to find the actual length in meters in real life. So those dimensions are 750 meters by 500 meters. So here's our answer. listed as length by width. The actual parking lot would be 750 meters by 500 meters. Number 6, the area of the parking lot on the blueprint is 10 centimeters by 15 centimeters, equal to 150 centimeters squared. What is the actual area of the parking lot in square meters? And so here we can see how we calculate the area of a rectangle and multiply the two dimensions. So how can we find the amount of square meters inside the actual parking? So remember how each of these questions will build on the other. In question 5, we found out that we have a much bigger parking lot in real life than on paper that measures 750 meters by 500 meters. So how would we find the area of the parking lot? We would find the area of the parking lot by multiplying its dimensions. 750 meters times 500 meters will give us the meters squared of area in the parking lot. But before you do anything crazy, let's think about how this is a simpler problem than it may appear. Let's recognize that we're multiplying by 2 powers of 10. So first of all, we're going to bring these zeros with us. We're going to bring the 1 zero from 750, 2 zeros from 500. So we know our answer is going to end in 3 zeros. That leaves us the problem 75 times 5. So here we've multiplied 75 times 5, and we have 375. So really not a difficult multiplication problem. It boils down to 75 times 5 and bringing with us the zeros from each of the numbers. So we have an actual parking lot area of 375,000 square meters. 7. A ski shop is having a start of ski season sale. Every item in the store is advertised as 1/5 off the original price. If a ski jacket is marked with a sale price of $72, what was the original price? So in class we approached this type of problem using a tape diagram, or if you choose an equation. So into how many parts are we going to divide our tape diagram? So here we've divided our tape diagram into 5 sections, and it says 1/5 off. So that 1/5 off is something we don't pay. So leaving what fraction of the model we do pay. That would mean we are paying 4/5 of the original price. So which of these do we know? Do we know the sale price or the original price? If we search the problem, it says the sale price of $72, and then the original price has a question mark by it. So we don't know the original price, and we're given a sale price of $72. So this 72 is being shared by how many boxes in our tape diagram? So it's being shared by 4 boxes. This is the part of the diagram we do pay. 72 divided by 4 is 18. So that means originally this price was made up by 5 18s. They took one of those 18s off for a sale price of 72. But for the original price, we had 5 18s. So we can multiply 18 times 5 to find the original price of $90. So before the sale, the original price equals $90. And that, scholars, takes us through problem number 7 of your test review tour. Tune in for the part 2 of the tour for problems 8 through 15.